All right, there you go. You're good to go.
All right, yeah. Hi everyone. Welcome to Introduction to Reinforcement Learning. I'm Jim. I'm really excited to introduce this topic to you today. So first of all, let's discuss what reinforcement learning is. Can you raise your hand if you've heard of reinforcement learning before? Okay, and keep your hand up if you think you're comfortable in explaining what it is. Okay, yes? Do you want to go out?
Oh. Okay, it's kind of similar to like how you do other like machine learning, but the idea is like you're trying to attribute some value to like some state across some arbitrary task, and then you're implementing the value.
Yeah.
Alright, I'm going to take a shot. I'm going to assume like you have some kind of like goal or some number for it to like achieve, and as it gets closer, you want it to repeat what it does to reach your goal. So basically like you're rewarding it for getting close to what you set.
Yeah, exactly. So you described like two of the elements, right? The state and the reward of the environment. So reinforcement learning is essentially when a machine learning model is put into an environment and has certain factors such as a state, rewards, actions, among other things, and it wants to optimize for the highest reward. And so that's illustrated.
Oh, my bad. There you go.
Cool. Yeah, that's illustrated in this diagram here. So the agent is the machine learning model, and the environment is the environment which it's acting in. So when the agent takes an action, AFT, it changes the environment, and that environment gives back two things. First is the new state, and the second is a reward. And so for every action that an agent takes, it'll get a reward, and it'll also change the state. Does that make sense? Another difference between reinforcement learning and other machine learning paradigms like supervised learning and unsupervised learning is that in reinforcement learning, the model generates its own data set. So for example, in supervised learning, you have to classify things like if you want to detect cats versus dogs, you have to label a bunch of images as cats or dogs. But in reinforcement learning, the model is placed in an environment, and by taking actions within the environment, it can learn the reward functions associated with certain actions in different states. And thereby it generates its own data set by taking these actions and storing like the state action pairs along with the rewards. It can generate its own data set and then sample from that. Okay, so here's some examples of reinforcement learning. One is the very popular AlphaGo model, which beat Lee Sedol, the world champion, in 2016. This is really, really monumental because Go is actually an incredibly difficult board game to solve. So the number of legal Go boards is somewhere on the order of like 10 to the power of 170 or so. For reference, the number of atoms in the universe is about 10 to the power of 80. And so the number of valid Go moves is about like 10 to the power of 80 times 10 to the power of 80. So it's like if you took all the atoms in the universe, laid them in a row, and then had like the number of atoms in the universe, number of those rows. So you have like a grid where like it's like not number of atoms in the universe by number of atoms in the universe, and that's like the number of like tiles on that grid is still less than the number of legal combinations of Go. So this is actually like a very complicated game. Another is StarCraft, so this is called AlphaStar. Google later like launched a model to beat the world champions at StarCraft, which is a kind of video game. Now this in robotics. So sometimes we want like robotics to grasp objects, for example. And so we can use reinforcement learning to train a robot to automatically like grasp different types of objects depending on the characteristics. So and like there's going to be an associated reward with like dropping the item into like the basket, and the robot will need to change its grip style depending on what it's picking up. So for example, if it's picking up something very long like a stick, you might need to grip it like close to the center. Whereas if it's gripping something like very squishy, like a rubber ball, or something even squishier than that, it might need to like soften its grip a little bit, not to like let it slip if it's slippery. And finally, we have ChatGPT, which actually does use reinforcement learning in a paradigm known as reinforcement learning from human feedback. So this is where in ChatGPT, because it's responsive, a human actually annotates like different outputs generated by the model. So what OpenAI did is they took the model, had it generate 4 outputs, and then a human then ranks those outputs of that model on the same prompt from best to worst, and they trained the reinforcement learning algorithm on that data in order to get it to generate towards the best of those rankings pretty consistently. Okay, so now we're going to go into a mathematical formalization of this problem. We discussed essentially what the state and the action and reward like values are in a reinforcement learning environment. We're going to explain this in terms of mathematical formulations so that we can like derive an algorithm to optimize. So first thing we're going to talk about is something called markup chains. So raise your hand if you've heard of a markup chain before. Okay, great. So that's like about half of us. It's really good. So for anyone who doesn't know, or just to recap, you have a set of states S, which go from S0, I'll call this S0 as well, through Sn. And so these are just like discrete states that you can be in. Right? You also have a series of time steps, 1 through t. And so at every time step, you're going to be associated with a given state in that state set S. So for example, at time step 1, I could be at like the start state, like S0. At time step 2, I could be at some other state, like let's say S6, and so on. At every time step, I'm associated with a different state, or the same state. You can have states repeated as well. And yeah, you're going to change the state per time step, and you can also change the same state. This will be more evident when you see the diagram. And then the probability of being in one state depends only on the probability of being in the previous state, and not on like the states way before. This will also be more evident in the diagram. So this is a diagram of markup chain. And the example is of child behavior. So you can see the child could be in 3 different states: playing, eating, and crying. These are like S0, S1, and S2. And so there are arrows going from the nodes to each other, including to itself. So if you look at playing, it has a self loop, and so does eating, and so does crying. And so it is possible for a markup chain to have a node that transitions to itself. But oftentimes it's also going to transition to other nodes. So for example, if I'm at the state playing, then there's a 40% chance that at the next time step, I'll be in the state crying. And there's a 50% chance that I'll be at the next time step in the state eating. And a 10% chance that in the next time step, I'll be playing again. And so this is like a visual representation of a markup chain in which at any given time step, I'm going to transition into one of the other states with probabilities of these edge probabilities. Does that make sense? Great. Now we're going to talk about random walks, which is just like a random walk like along a markup chain. We're going to see this. So essentially, we're going to start at the start state, call it this S0, and we're going to transition states at random according to the markup chain. So can someone name like any random walk on this markup chain? And when we have a random walk, we have an associated length, but you can choose any length you want. Yes.
0 to 1?
Yeah, sure. So that's a length 2 random walk. And here, in fact, if you're at 0, you have to choose 1 because the probability of going from 0 to 1 is 1 or like 100%, right? Yes.
0, 1, 0, 1, 0, 1.
Yes, because you can go from 0 to 1 and then go back to this 1/2 probability and repeat indefinitely. Great. Another example of random walk might be something like 0, 1, 2, 1, 2, 3. And once you're at 4, you can only repeat at 4 because of the self-loop having probability 1. Is this clear?
Yeah, I think he had a question though.
Oh.
Do you have a question?
Oh, I was just saying, it can't go from like 0 to 2, it has to go through
Yeah,
1 in this
exactly.
example.
Exactly. So the markup chain has a structure, right? And you have to follow the structure. You can't just like jump between nodes randomly. You have to follow the edges. Great. So now we're going to discuss something called conditional probability. This is going to be a little bit of notation. So essentially, you have this probability again, and the probability of being in the state B given the state S is that conditional probability. So this bar in the middle is read as given. So what this means is that if you're in state A, what is the probability that you're going to transition into the state B? And so for example here, the probability of state 1 given state 0 is 1, or 100%. And the probability of the probability of state 3 given state 2 is 1/2. Does that make sense? Great. So for example, I think I already went over this, but the probability of being state 2 given state 1 is 1/2. Great, so now we're going to formalize our reinforcement learning environment. we call this a Markov decision process. It's going to build on top of a Markov chain. So the difference between a Markov decision process and a Markov chain is that we introduce a couple of things. So we still have our set of states S, but now we have a set of actions A, and we have an agent that can choose between actions. In a Markov chain, your results are determined by the Markov chain. You take a probability at every given time step. But in a Markov decision process, that's not necessarily the case. The agent has the freedom to choose between the action sets, between the actions in the action set. We also have a reward function, which we didn't have in the Markov chain. The reward is going to be something associated with the state, action, and next state. So this S prime just means the state at the next time step. And so a reward function doesn't necessarily have to use all of these three variables, but it can use up to these three variables. So a reward function might be defined solely in terms of like a state. So like if you're in a certain state, it might be better than other states. But it could also be defined in terms of like the action and the next state. This will be a little bit clearer later when we talk about stochastic functions. We also have a transition probability of P of S prime given S and A. So this just means the probability of going to the next state, S prime, given that we're currently in the state S and take action A. Yes?
Wouldn't the reward function have to take in at least one action and the state? Because if it was just the state, like how would it know, what action to reward?
Mm-hmm. So, yeah, that's a good point. You could, I guess you probably wouldn't reward only the state, but you could reward like only the next state. So like if I get to the next state, then like the model might like, or the environment might discard what action you took. It just matters that you got to that state. It doesn't matter how you got there. Does that make sense?
A little bit.
So like maybe I have like a grid, and certain like positions on this grid have a score of like, let's say 5. And it doesn't matter how you got there. You could have gone like down or right or left or up. But no matter how you got there, that score, that tile has an associated score of 5. Cool. Yes?
Isn't the next state dependent on the current state and the action?
Yes.
So the reward function is determining which action to take?
So the reward function is something provided to you by the environment.
Okay.
It's not something that the model knows. In fact, the model is trying to essentially learn a reward function. And so this is going to make more sense when we talk about stochastic functions, but essentially the next state is not deterministic based on the state and action in all cases. So like if I take a given action in a state, that could have different things on random chance. Like let's say I'm Mario and I jump and like try to hit a power up. There could be a couple different types of power ups. So that could have like a different outcome, even though I took the same action of hitting that block. Does that make sense?
Mm-hmm.
So yeah, some things are due to random chance. We'll elaborate more on this later. Yeah, so there's a transition probability, yes.
So I think you might like answer the question, so continue.
Great. So there's transition probability of going to that next state given that the current state in action. And so this, like if it's deterministic, like if we're in a grid and we like move right, then we're gonna move to the right tile, right? So that would be like a 100% chance of that like given state being reached in this manner. And what we want to determine is we want to determine something called a policy. We call this pi. And this is the conditional probability of taking an action A given the state S. So we're given the state S, and we want to output the probability of taking action A given that state. And our goal is to maximize the sum of rewards. So we have this reward function for a single state. We want to add up the rewards for like all states and maximize that. Does that make sense? Cool. Yeah, another aside is something called discount factors. So let's play a game. Would you rather have $99 today, or would you rather have $100 a year from today? Raise your hand if you prefer the $99 today. Awesome. And raise your hand if you prefer the $100 1 year from today.
Wait, there's a question that has to be back to. Are we able to invest the $99?
Yes, you can do whatever you want with the $99. So, anybody going for the $100 1 year from today? Okay, great. So all of you knew that even though the amount right now of $99 is less than the amount of $100, it's still wiser to take the amount of $99 today because there's an opportunity cost of that money if you wait 1 year. If you wait that 1 year, you could have done something with your $99, including invest it into like government bonds or stocks or any other kind of financial instrument that would increase your $99 to something above $100 most likely. In reinforcement learning, we don't have like investments, But there's still this concept of timeliness, of impatience. You want the model to go faster rather than slower. You'd rather have the model take a reward that's a tiny bit less than a larger, tiny bit more future reward. Does that make sense? Cool. And so we're going to quantify this as a discount factor. And so this is essentially a numerical quantity for impatience. And a common value is something like 0.99 or like 0.999. And the reason for this is essentially would you rather have $99.90 today, or would you rather have $100 a year from today? It depends on essentially how conservative you are with that kind of ratio. And at every time step t, we're going to be discounting by the exponent of this discount factor gamma. And so the discount factor we call gamma, we literally say gamma is equal to some value like 0.99 or 0.999. And the amount we discount each time step t is gamma to the power of t. Because we discount the first, the second time step by gamma, the next time step by gamma times gamma, and the next time step by gamma times gamma times gamma, etc. Does that make sense? Essentially, we're going to discount by gamma at every time step. So the cumulative discounting at time step t is gamma to the power of t. Awesome. Okay, now we're going to get to deterministic versus stochastic functions. So deterministic functions are the functions you've always been used to. So for example, f of x is x squared plus sine of x. And if you put in the same value of x, you'll always get the same output. For example, if you put in pi, you'll get pi squared plus 0, or pi squared, right? So anytime you put in pi, you'll get pi squared. That's a deterministic function. It behaves like you expect it to behave. Well, there's also a notion of something called a stochastic function, in which a function takes on a different value depending on different probabilities. For example, I can have f of x equals x with a probability of 1/2, and f of x equals negative x with a probability of 1/2. Now if I give you x equals 5, you can't tell me what the result will necessarily be, because it's a probability distribution. There's a 1/2 chance it'll be 5, and there's a 1/2 chance it'll be negative 5. Does that make sense? Cool. So we don't know what f of x is for sure, and many real-world phenomena are like this. Can anyone name one example?
Flipping a coin.
Yeah, I guess so. Flipping a coin. What would the x be?
Oh. Well, just x would be the nth coin flip, and being the nth.
Oh, and
coin
the
flip.
f of x is the count of how many coins are heads.
Yeah.
Yeah, sure, that works.
Well, it's partially deterministic. It's an algorithm, because.
Yeah, that's just how a
Yeah,
function
yeah.
works, I would say. So I would call it stochastic because it depends on chance. You can't necessarily have the same result every time. So another example would be the stock market, right? So a stock might move in a different manner, even if you if investors were seeing the same exact news, or even if the interest rate increased by the same percentage point. Stocks have some inherent randomness in them, and also particle motion. So if all of you are familiar with Brownian motion, essentially it's where particles randomly collide with each other, and this is modeled as a stochastic process. So now we're going to discuss something called expected value. Real briefly, let's take a scenario where you can play a game unlimited times. On every time you roll a die, and if the die turns up 6, you win $4. Otherwise, you lose $1. Would you play this game? Raise your hand if you would play this game. Okay, great. Are you raising your hand for playing the game, or raising your hand for a question?
Playing the game.
Do you want to explain why?
No.
Yes.
Don't play it.
I would play it 3 times because in those 3 times you would have a 5 out of 6 to the power of 3 chance of not winning once, and that's a little bit less than half. So which means if I play 3 times, there's about a half a chance that I would gain. Well, wait. Oh wait, no, that doesn't work out.
Yes.
Would the expected value be -1?
Yeah.
The expected value is not going to be -1, but it will be negative. I'm going to show you the calculation of right here. So expected value is the weighting of the amounts you win by the probabilities at which they occur. So you take 1/6 of a chance of winning $4 plus 5/6 of a chance of losing $1, and the sum is -1/6. And what this means is that on average, across many times, if you play this game, on average, every time you play, you'll lose 1/6 of a dollar. Does that make sense? Great. What if you won $6 every time the die turns up 6 instead of $4, and everything else is the same? So every time the die turns up 6, you win $6. Every time it turns up something not 6, you lose $1, and you can play it unlimited times. Raise your hand if you would like to play this game. Raise your hand if you would not like to play this game. Want to explain why?
Why? Because over time, there's an expectation that you will lose 1/6 of what you started with over time. I mean, of course, it might not happen, but there's a chance that you lose overall.
Okay, so I'm going to say that the expected value is 1/6 times $6, plus 5/6 times negative $1, which is $1/6.
You're saying if you won $6 as opposed to 4. I thought you meant if you won 6 after like 3 rounds.
No, if you won $6 as opposed to 4, yeah. If you won $6 every time the dice turns up 6,
Yeah,
otherwise you lose $1. Okay. I'm a little sad that none of you want to play this game with me, because I'd really like to play this game with you unlimited times. If you change your mind, let me know. Okay. But anyhow, you're also like all mathematically correct, because the expected value of random variable x is equal to like the values at which x can take, weighted by its probability, the sum of that. So this looks a little bit like mathematically hairy, but you can see like an example right here. All it is we're taking the probability at which something happens and weighting it by the value that we get from it and adding that up across all possible values that we can obtain. Notice that these probabilities will also like always sum up to 1 because like we're taking every possible probability of that happening. Does that make sense? Cool. And so we're going to mathematically formulate our goal of maximizing the reward as the following. We want to maximize the expected sum of rewards across all time steps, discounted by the gamma discount factor. This is what it looks like. So this looks a little bit mathematically complex, but if you think about it, it's actually nothing too bad. Another aside is that I don't want you to get too confused by notation, because it's just a way of expressing the concept. So for example here, the reward is written a little bit differently than we defined before, but it's the exact same thing. So sometimes people just put like the action as like a subscript instead of like inside the parentheses. That literally doesn't mean anything different. Sometimes like they call it being parameterized by the action. It doesn't really matter. Effectively, the reward depends on the state, action, and next state. So you're gonna take the reward, discount it by gamma to the power t, and you're gonna add that up across all time steps from t equals 0 to infinity. And because this isn't deterministic, we're gonna add the expected value. Does this formula make sense to everyone? Raise your hand if you still have questions. Yes.
Is this from like, is t equals 0 now, or like when the game started per se?
T equals 0 is when the game starts.
Okay.
Yeah.
Is the point of the discount factor to like punish taking a large number of steps unnecessarily?
Yeah, exactly.
Okay.
Exactly. Yeah, so we don't want to like waste a bunch of steps doing nothing and get like the same reward like later down the line. And instead we want to get those rewards like sooner.
What's the name of this formula?
This formula? I don't know if there's like a name for this, but I think if you just say like the expected value of like the sum of discounted rewards, like it's a little bit lengthy, but I think it explains like what you mean. Yes.
Would you say this is like analogous, like in supervised learning, like loss or cross entropy and stuff like that?
Yeah, so a little bit. This is a little bit like an inverse of a loss function. So a loss function, you want to minimize some kind of like square distance or like error or something like that, right? In this case, you want to maximize this target, like sum of discounted rewards.
What is big R is the reward, right?
Yes, big R is a reward function that takes in the values, the state, then action, and the next state. Any other questions? Cool. So now let's move on to the value function. The value function is something we're going to define as like the value of v in the given state. So it's literally a function v that operates on a state s. It's that simple. So let's take an example of a game. This game is called Frozen Lake, and it's an environment in OpenAI Gym. OpenAI Gym is a collection of environments and reinforcement learning like infrastructure that OpenAI has set up so that you can run reinforcement learning models and train them to experiment and determine which models perform better. This is also often known as a game called Grid World. Essentially, you're in a world with a grid, and you can take actions that are like moving right, down, left, or up. So in this frozen lake environment, you can move in whatever direction you prefer. And you're on a frozen lake, you can move across like these white tiles, but if you hit one of these blue tiles, which are the holes, then you die. And if you hit the treasure chest, you win. So now it can be pretty obvious that the reward of being like in the treasure chest state should be like 1 or something above 0. And the reward of being in a hole state should be something less than 0, like -1. Does that make sense? Great. And so we can define this value function of being in those states. So like the state S5, which is this hole here, will have the value of -1. And the state S15, which is treasure chest, will have a value of 1. So what about these black states? What I mean by black states is just these states where the text is black as opposed to like red or green. What are the values of those? Does anyone want to give a guess? Yes.
I don't know if it would be able to see this, but distance towards the chest would be like the reward value, or like, I guess kind of the reward value, or also just the state value is the amount of tiles it is away.
So if you were to formulate it that way, then what would the
Sure.
reward be of being at state 14?
Like very, like a pretty close to 1 number, I'm assuming.
Pretty close to 1. What about the reward being in state S4?
Like also above 1, but probably closer to like 0.1 or like 0.3.
Okay, so like when you're further away, the reward should be lower, right?
Yeah.
Yeah, that's absolutely correct. Because if you're farther away, the reward of like being in that state, you should not really target that state as much because like it's farther away. You want to get closer. The closer you are to the state S15, the higher your value is going to be. Does anyone else want to provide input? What do you think should be the value? Yes.
Well, in this case, that would work, but if you didn't know like the layout, like for example, there could be like an impassable
Oh,
wall.
but the thing is, the value function, let's say the model doesn't need to know it, it's trying to learn it, but like it exists. So we can just define a value for a state, even the model doesn't know it yet.
Oh, okay, well, in that case, not necessarily the closest, because there could be like, perhaps like S13 is like impossible to get out once you get in, for example.
Sure.
And so you wouldn't want to strictly do it by distance, but in this
Yeah,
case,
yeah.
distance would work fine.
Yeah, in this case it'll work fine. And that's a good caveat. Some environments are going to be more complicated. If there's like traps, then the reward of that state should be pretty low, even if distance is pretty low as well.
Can you distinguish between the reward and the value function?
Yes, the reward and value function are totally distinct. The reward function is something provided to you explicitly by the environment. When you make an action in the environment, it'll give you a literal like reward value. The value function is just something we're determining to help us like formalize a solution to the problem.
I guess I'll wait and see.
Okay, sounds good. Yes.
So the number we just talked about where like on the treasure chest would be 1,
Yes.
and like as you get like further and further away it would be less.
Yes.
Would that represent the state or the reward?
That would represent the value. So again, I want to point out that like the reward is something given to you by the environment. The reward that the environment gives you of being in S15 is 1. The reward of being in S12 is -1, and the reward of being in any other state is 0, because you don't get any reward if you're just standing on some like icy lake. The value function, however, is something separate from the reward. The reward is something given to you by the environment. The values function is something that you can determine. But in this case, we're defining it as essentially like the value of like our agent being in a certain state. It's like kind of like a model for the reward. We already have the reward, but it's like a model of like how valuable it is to be in a state, aside from the immediate reward. So like the reward gives you the reward of being in like an immediate state, action in the next state, but the value is going to tell you a little bit more. Like the value of being in a state farther away is high, you still want to be in that state. Yes.
Maybe like the probability that you reach the end goal by a certain time step, given that you're in that state currently.
Yeah, that sounds like a good idea. You want to maximize your probability of getting to the treasure chest. In this case, that's just like getting closer for the most part. But yeah, these are all like ideas. The way we're going to define this is that we're going to define this as a discounted value function, assuming that you take the optimal future policy. So if you're at state 13, the value is going to be the value of state 15 discounted twice. Because you're assuming that you take the optimal policy, which is going twice to the right. And that will be 2 time steps, which would take a discount factor of yes. So for example, the value of being in state 15 is 1, the value of being in state 14 is gamma, the value of being in S13 is gamma squared. What about S9? Yeah, gamma cubed. Okay. And then in S8 would be power 4, gamma number 5 for S4. In the start state, S9 will have gamma power 6. Does that make sense? So we want to define this value function recursively, and then we can actually like fill in the entire. All right, we're going to extend this a little bit to something called the Q function or quality function, because a value function tells us the value being in the state, but it doesn't tell us how good it is to take a given action at that state. So we're just going to add a parameter to our function A for action. And so we define a function Q to represent the quality of taking action A at state S. It's going to look like Q of S and A, so it's just like V of S, but with an action A. And let's ignore the discount factor just for this slide. If we take like the action of going from S1 to down, taking the action down at state S1 is -1, because we're going into the state that has value -1. Does that make sense? Even though the state S1 has no inherent reward, by taking the down action, we're like getting ourselves into a bad state. And so the Q function that we're modeling, like how we should optimize our model for, is going to be -1. Yes?
So would the Q function just like return what the value is going to be given like the previous state and that action?
Yeah, exactly. In this case, like you can just think of like the Q function as being like, if you take that action, then like what is the next state, and like what is the value of that at that state. It can be a little more complicated than this in real scenarios because of stochastic like processes. So like for example, there's a notion of slipperiness, where like if the character is like moving in a certain direction, or they want to move in a certain direction, you might slip and accidentally move in a different direction. In that case, you have to account for the probability of moving in the wrong direction in your calculation of the Q value.
Would it just be an expected value
Exactly.
function?
Yeah, you exactly. You want to optimize expected value. Great. And similarly, the Q value of being in state 14 and moving to the right is 1, because you get into the treasure chest if you ignore the discount factor. Great. Now let's consider like with the discount factor. So the Q value of being in state 14 and moving right is it's gonna be 1 time step away. So it is going to have the discount factor gamma as the Q value at the same action pair. Similarly, the Q, this one's actually not same. Does anyone want to explain why Q of S14 and up is gamma cubed, even though S14 is only 1 away? Yes?
It would take 3 steps to get to the goal, because you have to go up, and then back down, and then back right.
Exactly. If you take the action up, you've actually like made a misstep. And so like essentially what this is saying is that the Q value of taking the action up at state 14 is gamma cubed, which is less than the Q value of being in state 13 and moving right, even though like 14 is closer to 15 than 13 is. So it's better to like, it's essentially like really bad to be in a good state, but take a bad action. That's what we want to express with the Q value. Similarly, the Q value of being in state 13 and moving to the right is gamma squared, because if we take optimal actions, it'll take 2 time steps to reach it. For S9 and moving down, it'll be gamma cubed, and so forth. Okay. If we start at the initial state and move down, our Q value is going to be gamma to the power 6 away. Yes?
I'm a little confused because I thought Q would return like what it like your value is gonna be in the like next state. So like for S14 right, would it be like 1?
It does, except we're discounting by the discount factor.
Oh.
So at every time step,
Yeah.
the number of time steps it takes, we're going to take time step to the power of t.
But how is the,
Yeah. Yes.
well, actually, never mind. I understand.
Any other questions? Great. Does this make sense to everyone? The formulation of the Q value and like value, the Q function and the value function is really, really important, because we're going to start ramping up really soon. So if you have any questions, just ask. Yeah.
Okay, so are the Q function and the value function things that our model is trying to optimize? Is it like, what is the separation? I know it's separate from the reward, but is it trying to find out both, or like? how does
So
it exactly factor?
the Q function and the value function are handy concepts we can use in constructing a solution. the reward is something the environment gives us explicitly.
So when you say they're handy concepts, like they're not actually, like how are they used by the model? Isn't this my question?
So you're gonna see this really soon.
Okay, okay.
But like, briefly, if you have a table that has the Q value of every state and action pair, then at that state, if you take like the action with the highest Q value, then you will always take the optimal action, right? And we'll go over into this in more depth a little bit later.
So is your model gonna try to find out that table?
Yes.
Okay, okay. That's
Are we supposed to just know, or I guess, what the value or Q is for?
So we're gonna explore this real soon as well.
Okay.
Yeah.
That's what's hard.
Yeah. So to do that, we're gonna go up back to this guy. Does anyone know who this is? Yes.
he's the guy that's really good at probability.
Yes. This is Richard Bellman. He's the inventor of dynamic programming, which is used in our solution to the stream-form single learning problem. He's also known for some other things like the Bellman-Ford algorithm, if you've heard of that. It's like the shortest path when there can be negative edge weights. And the Bellman equation, which we're going to look at right now. So the idea of the Bellman equation is to express either the value function or the Q function recursively, assuming that the best action is taken at every future time step. So this is what it looks like. And so this looks like a complicated like mathematical beast, but if you break it down, it's actually not that bad. And it's actually pretty concise if you look at it bit by bit. So first, we're defining the value of being in state S as the maximum of like the Q function across all possible action state. This star just means like, it doesn't really mean anything too significant here. You can just pretend the star is not there essentially. But like, the star is like what we're updating to. Like V of S is like the theoretical amount, the theoretical value of state S is, and star is just like what our program has. Because it won't necessarily have like a theoretical amount. We're going to calculate it through this means. So the value of being in the state is equivalent to the best Q value at that state across all possible actions at that state. Does that make sense? Okay. In our formulation of Q value, we take the immediate reward of being in that state, action, and next state, and we're going to sum this across the possible states. And we're going to add the discount factor times the value function of the next state. So what this means is that we're going to consider the value of the next state. We're going to discount that by a discount factor gamma because it's one time step away. Does that make sense? So we're adding the immediate reward to the discounted sum of future rewards. This sum here is across the probability transition function. So this t is just the transition function. It's the probability of going to state S prime given the state S and A. So it's written a little bit differently in this notation, but it means exactly the same thing. And we're weighting it by the future states S prime. And so this is very, very similar to expected value. If we recall like the summation there, and the weighting across the probability. So t is a probability, we're weighting it across all possible S primes. And that's how we derive this Q value. Does anyone have any questions on Q function? Okay. And then this is nothing but putting these two together. So do you see how if we take Q star of S and A and put it right here, we get max of A and everything else? It's just some substitution there. And so we derive these three equations. We can recursively define the value in Q functions. This is called the Bellman update, also called the Bellman equation, Bellman backup, many other names as well. Any questions on this slide? Great. So now we're going to discuss the algorithm that we're going to use to solve a reinforcement learning environment called tabular killing. This is exactly what it sounds like. We're going to create a table of possible Q values for every state and action pair, and the model will just pick the best Q value at any given state. So whenever we're at a state S, we have like a row of like all the Q values for every different action. We just take the highest Q value in that row. Whatever action that's at that column, we're going to take that action. So this is what it looks like. So we have the actions across, and we have the states up and down. And so at the state S1, I might have Q values of like, let's say 1, -1, 0, 0. In that case, I'll take the action gain 0. Does that make sense? you want to take the best action. If you have this Q table, you want to take the action in the row like of the state that you're at with the highest Q value.
Do these values not affect each other?
These values are completely independent, or they're not technically independent, but you can treat them as independent when you're making decisions.
Yeah, 'cause like say S1 A0 takes you from state S1 to S2. Would Q S1 A0 not then be related?
Yes, it will be. It'll be related exactly in this manner. But the idea is, even then, you'll still approach like higher and higher Q values essentially. The reason it'll be higher and higher Q values as you like progress like towards the treasure chest is because there are less time steps needed to get there, and so it'll be discounted less. Does that make sense? Cool.
We have a question online.
Yes.
So if there's a pair of SA that tends to lead to the a reward being infinite, but has a very low probability, would the agent be misled to thinking this state has a high Q value when we probably don't want to visit that state?
So what's considered the infinite reward? Like the reward function of being in this state, action in next state, like I don't think that can necessarily be infinity. So what is the infinite reward in this case?
You heard that question. If you type, I'll ask him. Go on. Yeah, sorry, that was the person in chat.
Okay, a few other caveats we need to discuss before implementing these algorithms. The first is the challenge of observations. And so the idea here is that everything we've discussed so far is called a fully observable state, in which we know the exact state. We know like every single tile, whether it's a frozen lake, whether it's a hole, or whether it's a treasure chest. And this is like cheating, because in the real world, you don't get a fully observable environment. There's going to be parts of places where you can't see. This is called a partially observable state. Instead of knowing the state ST, you only know the observations OT. And so, for example, like if we're training like a self-driving car, and we see like a cheetah, we might see the cheetah only in certain frames, but not in others. But the cheetah still exists in the state of the world. Does that make sense? Great. And so essentially, the environment and agent interaction is going to look a little bit more like this. We have the environment. It's just the transition probability of going to the next state given this current state in action. And it's going to give our agent a reward for every action that we take. And it's also going to give the agent an observation instead of the full state for every action that we take. And then the agent itself can update the policy pi of the action given the observation instead of the state. So essentially, instead of getting the state for the agent, we only get the observation because we don't like have full observability of the environment.
Yeah. Oh, also to their question, they said, so like, I think what they're saying is like, if there's like a really low probability for like winning the lottery on that last part, but it's 0 most of the time you go there, is there anything for like to combat that? Or like,
Okay. Okay, so the answer to that is that is in the equation. So here, we have the probability like transition function, right? So what you're saying is like the reward function is like, let's say 1,000,000, and the probability transition function for that like possibility is like, let's say 1 in 2 million. So if that's the case, then when you multiply 1 in 2 million by 1,000,000, you only get 1/2. So even though the reward is really high, because the probability is so low, the actual reward that the model learns is pretty low. And so if there's a better option, it won't necessarily like be greedy and take only like the possibly really high value.
okay.
Does that make sense?
Yeah, that makes sense to me. Thank you.
Do people implement like methods for like risk aversion for like risky scenarios? Because say in that scenario, like your reward is like 1 in like 10 million, but it's only like a 1 in 2 million chance to happen. The like AI might still see like a 5 reward and be like, this is the best way to go, even though it's only beneficial so rarely. Do people usually code around that?
There are some methods for risk aversion. We're going to talk about one like just a little bit later. But the main thing is that in real life, there actually aren't really like, or like in most games, there aren't really like lottery types of rewards. Like they're, like if you're playing Mario, like what's the like win the lottery reward? Like I don't know.
Get to the warp zone.
Yeah.
Okay. Yeah, so maybe there are certain like pretty high rewards, but typically like there's not like very extreme scenarios. Like the majority of the rewards are like pretty low. Yes.
Do you ever like normalize the rewards, or will that defeat the purpose?
So, as far as normalizing, you can like take in what the reward function and do whatever you want with it. So the environment will give you like a fixed reward at every like state, action, next state. But you can like adjust your like desired reward to whatever you want. Yeah. So that's like up to your model implementation. Great. And so this is an example of partial observability in our frozen lake environment. We can see the state S0, but we don't know any of the other states. Does that make sense? We don't know where the holes are. We don't know where the treasure chest is. All we can see is the current state we're at. And so if we're taking an action, we actually will only know the effect of that action from the environment updating. Does that make sense? Right. And so we don't know what's at a state until it's traversed. And we can consider an example where we start at the state S0, and we take the action right. And that's going to get us to the state S1. So the only way we knew this is by taking the action to the right, moving to the right. And how do we know to take the action to the right? Initially, the Q table is all zeros. We don't know what the Q table is. It's not provided to us by our environment. And so actually, we have no way at all. It's like if I drop you in this like world, this map, and cover up everything except for S0, how do you know where to go? You don't. So you just have to take random actions at first. This is exploration. Once you've like gone to a place on any of those states, you like know what it is essentially. That's like in your memory essentially. Does that make sense? So at first you have to take random actions, and we're going to define this concept called epsilon greedy to navigate this environment. So this is the idea of exploration versus exploitation. At the beginning of a game, you want to explore your environment as much as you can first because you know nothing about it. So like, let's say you're in a jungle or rainforest or whatever. At first, like there's nothing you can do but explore, right? See what resources there are. Like maybe there are berries, maybe there's water, whatever. But once you have like those berries and that water, you have the choice to either like gather more berries and more water, like exploiting the environment, or you can go and discover new potential resources. So at the beginning, you typically want to explore as much as you can, and later on, when you discover like 100 different things, you want to exploit more often. Does that make sense? Great. And so we can like formalize this as an exploration factor epsilon. So this is a number between 0 and 1, and we're going to encode this like exploration at first, and then exploitation later on. Another thing is that to encode this like the strategy that we want, we're going to have epsilon decay either exponentially or linearly. So essentially, like epsilon might be like 1 at first, and then be 0.99 next in the next time step, 0.98 in the next time step, 0.97, and so forth. That'll be a linear decay by decaying by 0.01 at every time step. Or it could be exponential decay, in which it'll be like the discount factor. It'll be like epsilon equals 1 in the first time step, then 0.99 in the second time step, then 0.99 squared in the third time step, and so forth. And the action that you're going to take at any time t is going to be either a random action with probability epsilon. So at first, like it'll have epsilon equals 1. You're just going to take random actions all the time. But pretty soon, you're going to get to a state in which like you have your Q table. You might want to take actions according to your Q table instead of like random actions. And so in that case, you're going to maximize over like your Q values of the actions with probability 1 minus epsilon. So this is like taking your Q table approach with probability 1 minus epsilon. And so at the beginning, your epsilon is going to be really high. You're going to take mostly random actions. At the end, your probability, your epsilon is going to be really, really low, and so you're mostly going to exploit your Q table. Does that make sense? Awesome. Now we want to talk about risk, which we mentioned like just a little bit before. We already discussed the slippery frozen lake. To formalize this, like if I'm trying to move into a direction, there is a 1/3 chance that I move in that direction, a 1/3 chance I move orthogonal like 90 degrees, and a 1/3 chance I move orthogonal in the other 90 degrees. So if I want to move up, there's a 1/3 chance I move up, a 1/3 chance I move left, and a 1/3 chance I move down. If I want to move left, then there's a 1/3 chance I move left, a 1/3 chance I move up, and a 1/3 chance I move down. Does that make sense? So what if an action that you took was optimal, but because the lake was slippery, it actually forced you to slip into a hole? So for example, like you move to the right to avoid a hole, but because it's slippery, you actually fall down into the hole. does that mean that your action was wrong? No, it just means that because of stochasticity and risk, you hit that hole even though your action didn't cause it to. And so basically we don't want to penalize the model too harshly for that risk happening. And so for this, we're going to introduce something called temporal distance learning. This sounds fancy, but it's really not. Temporal difference learning. And the idea is that the model might be wrong when it takes a given action. So if it gets to a reward, it might be a reward that's a little bit, very close, and so it gets that reward very easily. But instead, it should actually seek out a farther reward that's much higher. We're going to introduce something called learning rate alpha. This is very similar to supervised learning. The idea is that we don't, when we experience a reward, we don't want to add the full reward. Instead, we want to add a part of that reward that is alpha. And we're going to have a temporal difference between the value of the next state and the current state, instead of just taking the value of the next state itself. And so this is what it looks like. The value at a given state is the value, say, plus alpha, which is our learning rate, multiplied by the reward at that state, plus the difference between the discounted future sum of rewards and the sum of rewards current. Does that make sense? Raise your hand if you have any questions. Yes.
So what are some example alpha values, or typical alpha values?
Yeah, this actually varies quite a lot. You can really use who you want. You can use 1/2, you can use 1/3. It doesn't really matter too much, depending on how much you want to bias your model.
So if you make it super high, then what's gonna happen?
If you make it something like 0.99, then whenever it gets a reward, it'll learn that reward extremely quickly. Okay. But that might be a local optimum, right? It might be a much better reward for them.
Yeah.
Okay.
Just we have 5 minutes left, so
Okay.
can we so if you guys have questions, we will be here after. You can ask them as well.
Yeah, sounds good. Okay, and so that's actually the time you have the full algorithm right here. That's what it looks like. So actually, this looks pretty complicated, but in fact, it's describing the entire algorithm essentially 7 lines. So if you break it apart, it's actually not that bad. Everything we've discussed here. So first, we have an exploration schedule for our epsilon greedy approach. At the beginning, we want to explore a lot. Later on, we want to exploit a lot. We want to initialize the Q function, which is the Q table to all values of 0 at the beginning, because we don't know anything yet. Then we want to measure the initial state, x0. This is given to us by our environment. It's like that top left corner in the example grid. Then, at every time step, starting from the time step 0 through the finishing of the game, what we want to do is first, we want to take an action according to our epsilon greedy algorithm. So with probability epsilon, which will be 1 at first, we will take a random action within the sample space, random action within the action set that we're given. And with probability 1 minus that, we're going to exploit our Q table and take the optimal value in there. We're going to apply this this action. So essentially, we're going to give it to the environment and get back a reward in the next state. And finally, we're going to update our Q value in the Q table through the Bellman update. So we're going to add the previous Q value plus alpha, our learning rate, times the reward at that time step, times discounted maximum Q value at the next time step, subtracted by our current Q value at the time step. And so this is the temporal difference. This is how we recursively update the Q value in the Bellman update. And by repeating this until convergence, we get an optimal policy. Any questions? Does the full algorithm make sense, everyone? Yes.
I have 2 questions. The exploration schedule, is there some kind of standard?
Yeah, so you can either use linear or exponential decays, typically the standard. Yeah.
And then just in general, at least for the grid problem, what would be the time complexity?
The time complexity. Yeah, I guess it's actually the next slide as well. Time complexity. I'm not really sure actually. There's a lot of stochasticity involved, so it's really, really hard to say.
Yeah, it'd probably be based on time step.
Yeah, I think it's really hard to say. It's also kind of hard to say in general for machine learning algorithms, what's the time complexity of learning the environment?
Yeah.
It's I think really, really hard to quantify. I definitely don't know the answer. Yeah. If we want to implement this, we can use the OpenAI Gym frozen lake environment, which we can import into our Python. and we can use like NumPy, for example, to store the Q table very efficiently in memory. And this entire algorithm takes like less than 100 lines of code. Because of time, we're just gonna like look through it extremely briefly. So I'll maybe pull this up. Yeah, okay. So essentially we're gonna define this Q table class in which we have like our hyperparameters like size, alpha, gamma, epsilon. We can update it with all those values. And we're going to update the Q table at the state and action pair with like 1 minus alpha times etc. This is going to be our update of the Q value with like the Bellman update here, target. Run policy is just going to either like take a random action with probability epsilon or exploit the Q table with probability 1 minus epsilon. Epsilon is our scheduling. Depending on the iteration, we're going to like decrease the epsilon by the number of iterations. We have 1,000 time steps and so forth.
And
then here we just call OpenAI's gem to create the environment. We reset the environment to a known state of 42. This is just going to give us a certain configuration that's always going to be the same configuration of frozen lakes of holes every time. We initialize the Q table, and then for all of our steps, we're going to print some debugging info. We're going to run the policy. We're going to step through the environment, get back the reward in next state. If it's terminal, we'll execute some logic later. We'll update our Q table with all those values that we get back. We'll update epsilon with our epsilon scheduling algorithm. And if it's terminal, we need to reset the environment, and we'll constantly get the next observation. And
awesome.
Close the environment. That's all. We can maybe like show it in progress. I don't think we can see that.
I think we just go like this. And then you could talk over this once it shows.
Okay, yeah, so at the beginning, because epsilon is really, really high, it's going to take random actions the vast majority of the time. This is actually a very hard environment for it to learn in. But eventually it's going to learn like the Q values of like moving down here are like negative, and so it's going to like try to not do that. But it'll take a while to convergence. There's some debugging info that tells you like what iteration it's in. I think at iteration 500, it switches off the epsilon like randomness entirely, and will only exploit like the Q table. So it should like print the Q table every like 100 iterations or so. Eventually it will converge.
Yeah.
Yeah.
And I sat here and watched it, so.
Did it converge?
It converged when I ran it, yeah.
It converged, yeah.
How long did it take?
Probably around 700 time steps.
But like how long in like human minutes?
if it's 50 frames, so if it's like 60 frames a second, that's like a minute and a couple seconds.
Oh, it's just on the Q table.
Yeah.
Yeah.
Are we running this slowly, or is it?
Yeah. So each column's an action, and then each row is a state.
Are we like?
Are we just gonna sit here and watch those now?
Yeah. Are we like sleeping every few seconds? Why does it look like so slow?
It's slow because it's like for humans. Like otherwise it would just like dump and you wouldn't be able to like.
Yeah.
Track it. Yeah.
So when it decides to like explore with the epsilon value, is it like completely random?
Yes,
or
it's
does
absolutely random. It does not like
even
use
if it's
any
already
of the-
explored somewhere before, it'll just go there
Yes,
again.
it will because it's really dumb. It just takes a random
nice.
action.
I got that.
Yeah, it doesn't
What
care
did-
about any
Oh, this
memory or
one's
any
not-
Q table
yeah.
at all. Yeah.
It's getting there. It's learning.
It is
Slowly but surely.
It's doing that.
Yeah, it doesn't go into the top right one anymore. It doesn't look like it.
I think it's being too conservative.
Yeah.
Yeah.
It's like
We could change some values.
Not get in the top right one. That's nice.
We could change some values if you want. Oh no! Oh no!
Just figuring it out.
I'm sorry. That's my bad.
Oh!
Oh!
You made it once.
That's getting better.
There it is. That's 2 in a row.
You know, a minute, yeah.
He's avoiding He's afraid.
Yo! All right.
Figured it out.
So like, would this like, is there any chance of an overfitting problem with this type of learning or no?
What would it overfit on?
I guess just like, cause the state is, like for example, if he was in like, just like one right at the start, and like because of the positions the lakes are now, like the best move is to go down, and so like assuming that's a state and the action is down, it works here, but it wouldn't work necessarily like in a different setup with the legs being in different places.
Mm-hmm.
Yeah, sometimes you get like a local optimum where you just die the quickest as you can. So here it would just be like going down.
Yeah.
Yeah, like now it's just.
I feel like what he's saying is like, so like this will like sort of overfit to the environment that you put it in.
Oh, no, this is only on that environment.
Yeah.
We're only defining it for a given environment. It's
Okay.
going to learn in a different environment every time. Yeah.
Okay.
Not in general. Yes.
But couldn't it also, if you had an environment where maybe there was one path to the goal, but then if that, depending on the exploration factor, if it doesn't explore enough, it can maybe overfit to take a certain like path to the goal, gets to the goal, but it's a longer path.
Yeah, I guess you could. It's possible. In theory, the epsilon should allow it to explore enough. Like when it takes random actions, it'll figure out there's a shorter path. But it's pretty hard to follow because in a partially observable state, you don't know where anything is. You can't actually see that there's a shorter path because everything's covered up essentially, right?
Yeah.
So yes, I think in that case it is possible to learn like a locally optimal solution. But in general, like this approach is like a solution. Yeah, as you can see, it exploits only now. Like,
Yeah.
Because the Q values for those states are very high, it'll only take the same path. It knows like what to do now.
Okay.
This example is like interesting because like if it just when it was exploring at the start, it almost always dies because
Yeah.
there's just so many ways for it to die. So like it did kind of feel like once it gets like under the I don't know like row 2, block 3, it was always doing the same L path. Like it never
Yeah.
explored. I guess like it's just hard for it to get to that point of like any exploration left
Yeah, it
in the
really is.
schedule.
Yeah. Well, until you actually finally get that reward, everything in the Q table is negative or 0. So until you find the actual like 1, it's all going to be negative. So like the highest that it knows is 0 in the table.
Yeah. Yeah. Does anyone have any more questions on that?
Can we run it again with slippery?
Do you want
Kind of out of time.
Yeah, do you
I have,
wanna-
like,
let's-
2 more slides.
Yeah.
If you want, we can like run it with slippery a little like after everything's done. I guess right now we'll like go back to the slides because we are a little over time.
Yeah.
So yeah, does anyone have any ideas of what might be problems with tabular Q learning with this approach? Yes.
If the game is especially complex, doesn't it require a lot of memory?
Exactly, like tons and tons of different states, right? Yeah. Any other problem? Yes.
What if it's impossible?
What if what's impossible?
The reward is impossible. But it basically won't be able to figure out it's impossible. Because if you're given an unknown situation, it's potentially possible that's impossible. But it'll try forever.
Yeah, but I guess that's just like bad game design because there's no model at all. Like even the state of the art model cannot possibly win in that environment.
But it should be good if you could figure out if it's impossible though, right?
I don't think any reinforcement learning algorithms are capable of giving up yet.
No.
Yes.
It seems like it only works if there's like a finite number of actions you can take.
Exactly. That's a really, really good point. So those are the 2 points. The first is this only works for discrete state and action spaces. If you have an action that is like a number, let's say like you want to output like the amount of force you want your thrusters to on a rocket to output, like 1.2 or like 7.8. Like these are continuous values, and you can't really represent this in a table anymore. And so
Wouldn't you
Q
just
table.
find a maximum?
What?
Wouldn't you just find like a maximum or a minimum?
But how would you like tell? How do you consider like the Q value of like how many thrusters on at 1.3? Yeah.
Could you just make discrete metrics and then fine
Yes,
tune?
you absolutely could. So you could like tabulate like all the possible like thrusting velocities. So that is one like approach. Like for example, if you can go from like 1 through 10, you don't necessarily need to output like 5.5. You just output like discrete 5 if you want. But this does cause a lot of states, which is the next one. It's called the curse of dimensionality. This was actually formulated by Richard Bellman. And the idea is that if we were playing the game Atari Breakout, and we're learning from the pixels on the screen, and each pixel will convert to grayscale, and so it'll have a valid color like or brightness between 0 and 255. In that case, how many possible states are there? Well, there's 255 to the power of number of pixels on the screen, which is 300 by 200. And even though it's a really low resolution, the number of possible states is far, far larger than the number of atoms in the universe. We cannot possibly represent this in memory. Does that make sense to everyone? Yeah. So the curse of dimensionality essentially says that like the state space explodes exponentially like as a number of dimensions. And so the solution is to use a function approximator, which is neural networks. So one approach is to use a neural network to exactly like model the queue table. So you have like the input of like the state and action, and then it'll give the outputs of like all the different like queue like values for the given state you're in, and like all the possible actions as different like outputs. Right. So if you have like 4 different actions that you get taken, it'll give you the queue value for like each of those 4 actions as like 4 separate outputs. Does that make sense? So you can literally replace this with a neural network. It actually works like really, really well. And you also need to use another technique called experience replay, which we'll talk about next time. And there are other approaches that can perform even better, like policy gradients, active critic models, PRPO, proximal policy optimization. These are like much more advanced algorithms. Some of these are state of the art, like proximal policy optimization is what OpenAI used to beat human champions at Dota 2, which is a very advanced video game. And also is used in ChatGPT as well. And so we'll continue this study of neural networks for reinforcement learning and going into like the advanced methodology behind them in part 2. So that's like a neural network. Essentially, you have some input states, and like it'll be much deeper than this in practice and much larger than this. But essentially, the value inside every output node is the action's Q value.
Nice.
And continue this in part 2.
Go. Good job, Jim.
So yeah,
Nice.
Kyle and I will be here for any questions. Otherwise, enjoy the rest of your evening.